Hello and welcome to Equations of Motion. Let's have a little roadmap here. In this video we will be covering the concept of one-dimensional motion, what average speed is versus average velocity and how to do basic calculations, and the basics of acceleration, followed by some problems. In the next video, we will cover graphs of motion, and possibly in the same video, or maybe a following one, we will cover equations of motion. So here's our little roadmap. To start off, let's just define what one-dimensional motion is. It's quite simply movement in a straight line, which is mostly what you'll be using in grade 10, 11 and 12. So some examples could be left and right, up and down, north and south, and maybe a few other examples that you can think of. That is just simply your concept of movement in a straight line. Simply, if you can draw it on a number line, that is your one-dimensional motion. And remember, we can show it as a vector. That is mostly what you'll be using at this level. So let's have a look at average speed versus average velocity. So let's firstly define speed. What is speed? Can you remember? Good. Remember, speed is your change in distance, I use a d, over change in time. And there is no direction. For example, we could have it as meters per second. Remember that in physics, we can also write this as meters per second like that. Both are valid. This one tends to get used a lot the further up you go, but this one is still acceptable. However, velocity is displacement over time, and because displacement has a direction, your velocity has a direction. So we would have to write velocity. We would still use the same units, meters per second, but we would have to say direction, for example, west. Just an example. So let's use that in practice. This person starts at the origin. Remember, 0 is the origin. They don't have to start at the origin, but this example, they do. They will first walk 3 meters, right? Over, let's say, 10 seconds. Then they will walk in this direction. They will walk a total of 5 meters left. Let's say that they walk a bit faster this time. They also walk. Take 10 seconds to walk that distance. Now this is where the importance of the difference comes in. Shall we calculate the speed that this person took? Pause for a second and see if you can calculate the speed and the velocity and what the difference is. Good? Have you done it? Let's do it together. So, for speed, we need to take the total distance this person walked. So they first walked 3 meters, so we're going to write 3 meters. And then they walked 5 meters. So we're just going to add them together, and then we're going to divide by the time, which is 10 seconds plus 10 seconds, which I'm sure you can do in your head. So we've got 8 divided by 20. I know Takaza can do that straight away, but I will need to use my calculator. So we'll get 0,4 meters per second. That is our speed. Average speed in this case, because you can see he walked at different speeds, but our average speed is total distance over total time. And remember, you'll start off by writing your equation. What about our velocity? Our velocity, we need our displacement. Even if the question doesn't ask you to, you can just draw in your displacement vector, which is here. So what is our displacement vector? We can easily see that it was -2 meters, or 2 meters to the left. So now we know that our final velocity, our displacement, remember, write your equation first, -2 over, what's our total time? It's still 20, so we'll get -0,1 meters per second. But remember, we need to convert that negative. We can't leave it as negative, so we need to say that is 0,1 meters per second left. Good. Did you get both of those? That's good. Good. So let's talk about a little bit about average acceleration. Average velocity here. Sorry, this is average velocity. Average velocity works the same as just any average. You take, this is assuming, of course, that your acceleration is constant. If I knew, for example, my velocity here was 2 meters per second and my velocity here was 3 meters per second but negative, we could work out the average. Are we okay with that? We will apply that in some problems later. Good. Can you define acceleration for me? Good. You've defined it? So remember, acceleration is your change in velocity over your change in time. If you just said change in velocity over time, that is also acceptable. If your teacher in class provided a different definition, this is acceptable as well. My definitions are always a little bit different. We can, of course, show that in an equation. So change in velocity. What's velocity? It's v. What's our symbol for change? Is, of course, delta. Delta v over t, or delta t, you will see both, is equal to acceleration. Now, I will often draw a little arrow above those to show that they are directional. They are vectors, but it is not strictly necessary, but I do recommend it. For example, if we had, let's use our previous example. We will say that your initial velocity was 0 because he was not moving and then he started walking. So we can have our initial velocity. So our initial velocity was 0, wasn't it? Let's write down what we know. Let's say, in this example, we are just going to say that our average velocity was the final velocity, okay? Just for argument's sake. So we're going to say final velocity was 0,1. And remember, when we write these kinds of things down, we need to have a negative, okay? So we now can get our change in velocity. What else do we know? We need to know our time. Our time is 10 seconds. Remember to put your units. I forgot here. Good. Now, can we use this equation? Yes. We can say change in velocity is the same as, remember, write your equation first, F final minus initial over t will give us our acceleration. So negative 0,1 minus 0 over 20. That was just a mistake. I put down 10 instead of 20. Will give us our acceleration. So our acceleration is negative 5,0 times 10 to the negative 3. Of course, you can say 0,005. That's fine. Just not too many zeros. Otherwise, we're going to start getting lost. Meters per second. Or 5 times 10 to the negative 3 meters per second left. That will be our average velocity. Good, because we took this situation. All right. I have taken some key questions from this paper. If you can see it, you're welcome to practice any of the other questions that are here. Just pause. If it's difficult to see, write down what I read, pause, and try to solve on your own. Good. Let's start with question 1. Question 1 says, a car accelerates from 10 meters per second to 30 meters per second in 2 seconds. What is the magnitude of the car's acceleration in meters per second? This is a multiple choice question, but just because it's multiple choice does not mean you can't use an equation. 2 marks is still 2 marks at the end of the day. So, what key information do we have? Let's write that down first. We have our initial velocity, which is 10 meters per second. We have our final velocity, which is 30 meters per second. And we have our time, which is 2 seconds. So what can we use? We can just use our straightforward definition of acceleration. So acceleration is change in velocity over time, or in other words, final velocity minus initial velocity. I'll just put that straight in, but if you are struggling, use it. So our final is 30 minus our initial is 10 over 2 seconds. So we get 20 over 2. Now, because this is not maths, this is physics, you will not be given marks just for doing the maths. So you can just skip to the final answer, which of course will be 10 meters per second. This is obviously a multiple choice question, but it could easily be a worked question, in which case you would still get 2 marks. You would need to substitute correctly and give the final answer. If you were given any kind of directions, you would need directions, but this one asks for magnitude. So you do not need a direction when it asks for magnitude. What about another example? Let's do question 2. Andile drives from town A to town B and back to town A in 2 hours. The distance between town A and town B is 60 kilometers. What is the magnitude of the average velocity for the entire trip? Now, of course, you may already know the answer, but if you are not sure, let's just sketch this out. So he drives, we've got town A, town B, we're told the distance is 60 kilometers. He drives from town A to town B. Then he drives from town B back to town A. So what was his average velocity? Well, what was his average? What was his displacement? What was his final displacement? His final displacement was of course 0. So his average velocity must of course be 0. This is a trick question, so don't overthink it. Let us look at question 4. I don't know if you can read it. A truck driver is in a rush to deliver the load. She travels 45 kilometers at an average speed of 60 kilometers per hour. She returns along the same route at an average speed of 30 kilometers per hour. What is her average speed for the trip? Good. As a contrast to the question 2, this is a slightly more complicated question. Can you think of what steps we will need? Think about that while I sketch out the information that we have. So, do you know what we're going to do? This is just to tell you what we know. We know that the distance between her 2 points was 45 kilometers, and we know the speeds she drove at along between. So we know she initially drove 60 kilometers per hour for 45 kilometers, and then 30 kilometers per hour also for 45 kilometers. And remember, this is her speed. So these could be end to end, or like I've drawn it, it doesn't actually matter. Right, what are we going to do? Well, to find her speed, we need to find her distance over her time. Do we know her distance? Of course we know her distance. Her distance is just 45 times 2, which will give us 90 kilometers. Do we know her time? No, we have not been given her time. So we need to work out her time for the 2 branches. Can you do that for me? All right, now that you've worked out the answer, so if you weren't sure what to do, we first need to find the time. I found the time. I did it as one equation. There's nothing stopping you from doing it bit by bit. But seeing as this is a multiple choice question, you can take the shortest shortcut as long as you get the right answer at the end of the day. So I found the time for part 1 and part 2 by saying the distance, which we know was 45, divided by the speed, which was 60 in part 1 and 30 in part 2. Added them together, so my total time was 2.25 hours. I already know my total distance. We just say distance divided by time gives us 40 kilometers per hour. This may seem like a lot of work, but if you're quick, 2 marks is 2 marks. Don't just guess unless you're in the last 5 minutes of your test. Good. What other questions can we do? Let's go on to some long questions here. There is no atmosphere on the moon. Astronauts carried out experiments on the lunar surface in the early 1970s. In one such experiment, when a feather was dropped from rest, it fell 20.75 meters in 5 seconds. Calculate the average speed of the feather, determine the acceleration of the feather, and would the feather fall faster or slower if it fell through a vacuum on Earth? Good. Now, let's see, what do we know? We know the distance and we know the time. So can we work out the average speed? Of course we can. So what do we know? We know distance, 20,75 meters, and we know time, 5 seconds. I always recommend writing down what you know, especially when we get to equations of motion, because if you have written down what you know, you can normally identify what you don't know and what equation to use. So let's just do the speed is distance over time. Very simple. 20,75 over 5 seconds will give us 4,15 meters per second. Remember, it asked for speed, so that is the end of the story. Let's do the 6.1. 6.2 asks for determine the acceleration of the feather using the fact that its average speed is equal to its instantaneous speed at exactly halfway through the time. That is 2.5 seconds. Okay, what can we do? What equation do we need? Well, of course, because this is just your basic stuff, we just need acceleration is change in velocity, or in this case change in speed, over time. What do we know? We know that initially the velocity would have been what? 0. See, remember, dropped from rest. And our final velocity, the final velocity that we need to know, is 4,15 that we just calculated, meters per second. And what is our time? We are told that it is exactly that speed at 2,5 seconds. Good? So VF minus VI over T will give us 4,15 minus 0 over 2,5, which will give us 1.66 meters per second per second. Of course, are we finished? It did not say the magnitude, it asked for its acceleration. So we need a direction. Was it going up or down? Of course it was going down, so that's downwards. Of course, what does that acceleration represent? This is not part of the question, but this is your acceleration due to gravity. (6.3) Would the feather fall at a faster or slower rate if it fell through a vacuum on Earth? What do you think? It would, of course, fall fast at a faster rate. Why? Because the magnitude of acceleration would be significantly larger on Earth. On Earth, what do we normally round it off to? 9,81 meters per second. That's how fast the feather would fall in a vacuum on Earth. Remember, feathers fall slowly on Earth because we have air, and the air causes friction. But this is in a vacuum. Good. Question 8. A professional cyclist is able to reach a speed of 100 kilometers per hour by starting from rest and pedaling flat out for a distance of 3 kilometers along a straight track. Assume the rate of change of the cyclist's speed is uniform. Of course, rate of change of cyclist speed is your definition of acceleration. So you're saying he has constant acceleration. Firstly, show that 100 kilometers per hour is equivalent to 27.78 meters per second. Because it specifically says show, I don't want you to use your magical 3.6. You need to actually show working. So you would say 100. Of course, you would say times by 1,000. Okay? Divide by 60 times 60 times 60. So what does that give us? The wrong answer. I think I did something wrong. Give me a second. I'm not sure why I said 63 times. We just need 60 minutes and 60 seconds, not 60 hours as well. I don't know what I'm working with there. So of course that will give us our 27.78 meters per second. Of course you can put in some units here. You can say that's meters, you can say that's minutes and seconds, that's up to you. But what we're doing here is we're just expanding your magical 3.6 number. Okay. 8.2. Calculate the average speed of the cyclist. What equation shall we use? Shall we put up the equations again? Here we go. These are not your full equations of motion. You will not in general be given these equations. You'll be given the full equations of motion, but these basic ones you should know. They are your definitions. So in this case we are asked for average speed, which of course I'll just write this as average velocity because that's the equation I have here. Good. Or average speed is your final speed minus your initial speed over 2. No, this is change. What mistake did I make? What mistake did I make? I didn't copy my equations correctly. This is important because a simple mistake of not copying your equations correctly will make things come out wrong. Of course, as you know, your average is adding. When you make an average in maths, you add things together. You add when you average. Good. Sorry guys, it's a little bit late, but we will get there in the end. So what's our average speed? Very simple. We know his initial speed. Which should be 0. And we know his final speed, which we worked out here was 27.78. Divide that by 2. Will give us 13.89 meters per second. And of course it does say speed, so we don't need a direction. Calculate how long in minutes it takes the cyclist to reach this top speed. What do we need to do? 8.3. We know the distance is 3 kilometers. We know his average speed is 13.89 meters per second. So of course we can work out the time. We've got our little equation. I will always reorganize before I substitute. So I will say T is equal to distance over speed. So we've got our distance, 3,000 meters. Remember to convert. That's why I put the units, that's kilometers. You need to convert so that it matches. Over 13.89 meters per second will give us 215.98 seconds. It asked for the answer in minutes, so we need to convert back to minutes, which should give us, let's do, it actually comes out to 4.00 minutes. Of course, just 4 would also be acceptable because the actual answer, 3.60 minutes. Like I said, I am tired. I'm sorry, guys. It's just one of those days. If it asked for minutes and seconds, you'd of course convert that 0.6 to seconds, but otherwise 3.6 minutes is fine. This is the end. I will not make the other video tonight because I am clearly too tired to be doing this. And I will just make mistakes. So that's fine. What have we learned? Let's recap everything we've learned. We've defined what we mean by one-dimensional motion. Just to recap, it's not something you'll be asked, but it's just to know when we talk about motion in one dimension, we literally mean imagining it's on a string. We've got average speed and how to calculate it. Of course, we need to know speed is distance over time, and average speed is your initial speed plus your final speed over 2. The same thing for average velocity is your initial velocity plus your final velocity over 2. What is the difference? Of course, average velocity uses displacement and average speed uses distance. Good. What else did we learn? We learned acceleration. So we had acceleration is change in velocity over time, or the rate of change of velocity. Rate of change of velocity. That's our definition. And remember, your change in velocity is your final velocity minus your initial velocity. Have we covered all of these? Have we answered all the questions you need to? Good. Good luck for any future test.